Hello everyone, I'm Greg Weaver. Welcome to the Audio Analyst. Pardon me. Raymond Cook was a Royal Navy veteran. After World War II, as an electrical engineer, he was briefly hired as a design engineer at the British Broadcasting Corporation. He later took the role of technical director at Wharfedale, which was then a leading British loudspeaker manufacturer. But following corporate change at Wharfedale, Cook left to see his own ideas put into action. And so, in 1961, he founded his new company in a corrugated aluminum roofed, cement floored hut on the premises of a metalworking company that had been built on the banks of the River Medway near Maidstone in Kent, England, southeast of London, between London and Canterbury. This was, of course, the Kent Engineering and Foundry campus, whose initials, KEF, he appropriated to incorporate as the name of his new loudspeaker company, KEF. Now, today, in my second conversation with the remarkable Andrew Jones, he takes us back through his time at KEF, a period from 1983 through 1984. Now, for those who aren't aware, by the 1970s, KEF was leading the way in computer design, modeling, and acoustic research. And during Andrew's tenure there, at first as a research engineer under the inspired and visionary direction of Laurie Fincham, he eventually became KEF's Chief Engineer. Now, what many today do not realize is that in those days, KEF had become the hotbed of innovation, leading the field in speaker design, certainly in Europe, if not the world. Now, he covers a lot of technology and tells some remarkable and entertaining stories. So let's not waste any more time. Welcome, everybody. Once again, we have the amazing Andrew Jones. Last week was a lot of fun. I got a lot of feedback. The stories were so much fun. One longtime subscriber, Marcus, who now lives in Sidcup, which is southeast of London. I had to look it up. I'm not familiar with London. I'm not over there. But he said he was raised and schooled in Camberwell. And I don't know. I just think it was amazing that he had so much fun. If you go out and look at his comments under the video, it's amazing. But today, so we did your youth and your university time and your first research stuff, and we just got into KEF when we hung up last time. So I want to talk about KEF real quickly here because it meant a lot to me as a young guy on the sales, medium young guy on the sales floor. But so most people will know some of this, but I want to go through it. I'm going to use my notes so I don't get any dates wrong. Raymond Cook was an electrical engineer, and he founded KEF in 1961. And the story goes that it was initially headquartered in one of these, what you guys call a Nissan hut. I mean, the United States would call it Quonset hut. It's corrugated aluminum over on a concrete floor or something like that. But it was a small shop to get started with. And honestly, the thing that was amazing to me was, I forgot to mention, it was in, what was the river? It's near River Medway.
Yes.
Right?
Yeah.
And it's in
Maidstone.
Maidstone, that's it. Okay. But when he started this, KEF was totally science-based. I mean, it was all design and engineering, and by the 70s, KEF was leading the way in computer design, modeling, and acoustic research. KEF was one of the initial hotbeds of speaker design, certainly in Europe, if not in the world. I mean, I only have my own references for it, but I couldn't believe what was going on there. So you guys, KEF was the original source for all the drivers for the BBC LS35A.
Yeah.
And that was built by, Jim Rogers was building one, Spender was building one.
Yeah.
I think,
there's been a few others as well through the years.
But those were the two big ones, right?
Yes.
I had a pair of Rogers when I was a lot younger. But
the 1971 saw the introduction of the 105 reference. Now, I never got to hear it, but I saw the pictures, and it was unique in that it was the first loudspeaker, among other things. It was the first loudspeaker to have a separate chamber, a separate cabinet for each driver. And they were time aligned and phase array. I mean, it was a pretty interesting look. And I'll put a picture up. You'll see it when we do this here. But then 79 saw the implementation of a couple of things. What they called driver decoupling with the then 105.2, which it's a technique essentially that reduces cabinet colorations by mounting drivers with the use of what's called a controlled lossy compound. It's a isolation between the actual cabinet and the driver itself.
Yeah.
And then 84, which right after you got there, we saw coupled cavity base loading, which you talked about in your research stuff that you were doing with the stacks on the ships. And also, there was, what else was there at the same time? It was called, I'm sorry. Conjugate load matching.
Yes.
Which was the crossover optimization to keep a low stable impedance at the amplifier. And then 86, I remember the introduction of this, the KEF universal base equalizer, the KUBE. And that was, initially that was developed, to prevent phase lag at low frequency? Something like that?
Well,
Let me get to the last one, which everybody remembers, which is the Uni-Q in 1988. The Uni-Q was introduced, I think it was the C series was the first I saw it in.
Yes.
And that was an amazing idea. And we talked briefly about this before in passing. I'm not sure if it's going to show up in this particular video, but it's so logical when you think about it. But nobody had done it before that. So we go back. You came in 83. You got your formal job interview and you started there. And so if you want to touch on, what mattered with, I don't know if the 105 was important to you, what you saw had been done, or if you want to start talking about the really crazy stuff, like using the coupled cavity stuff in a loudspeaker instead of a 130 dB noise cancellation project. Because I had a pair of 104s, and I'll put a picture of those up too.
Yeah. Well,
I'm done talking. Please, you go for a while now.
Actually, but talking the 104 too, we should also talk about the original 104 and the 104 AB, because one of the things you've missed there is that in the old days, and unfortunately still to this day, because people don't seem to understand when they're doing crossovers, we talk about what the phase overlay between the woofer crossover and the tweeter crossover is. And we talk about Linkwitz-Riley. We mentioned Siegfried.
Siegfried, yes.
So the Linkwitz-Riley crossover, where they're typically fourth order up to squared networks, and they give, for woofer to tweeter crossover, they give the optimum off-axis responses to match into the room. But when we talk about that, what we really mean is the electroacoustic response should be Butterworth squared, not the crossovers. And people still don't understand that. You can buy active crossover networks with Linkwitz-Riley electrical crossovers, which is utter nonsense. And this was what, one of Laurie's first major papers that he published and became the 104 AB, the acoustic Butterworth, meaning that the mathematical functions that define how the woofer section adds to the tweeter section to give a flat response and optimum off-axis responses is the transfer function from electrical in to acoustic out.
Okay.
So if the drivers were perfect and infinite bandwidth, then the electrical networks would be that function. But if the drivers were that perfect, you wouldn't need any crossovers in the first place. So it's the combination of the response of the driver, which itself is a band-limited system.
Right.
Woofers have a certain low frequency response, and they have a limited high frequency response. They'll start rolling off above 3, 4, 5, 6K, depending on the design. Tweeters typically get down to just below 2K before they
Right.
start rolling off. And so if you just put a Butterworth, for example, network onto those drivers, they will not add up correctly together because
Okay.
their own roll-offs mess up the phase response through the crossover point and, of course, the amplitude summation. So he clarified that it's the overall response. And so he showed that basically you define the overall response to be, let's say, Butterworth. Let's say third order Butterworth.
Okay.
And then the electrical network is the overall response that you want divided by the response that the driver has. And that gives the electrical response that you need. So since the tweeter is already rolling off at second order,
Right.
but you want an overall third order response, the driver has to start rolling off, sorry, the crossover has to start rolling off at second order. Then when you get down to the frequency where the tweeter is starting to roll off, you have to reduce your roll-off rate to first order so that overall you get to continue to be a third order roll-off, and ditto for the woofer. So that's what the 104 AB was. It was a third order crossover, but there's a bridging capacitor across the two series capacitors to convert it into first order. And that became a defining difference and improvement over the original 104.
Now, I never heard the 104 AB.
Right.
And so, I mean, for people who aren't crossover freaks, there's like Butterworth, Chebyshev, Linkwitz, Riley, and they're all different slopes and different. They're all different. So you guys can go out and dig that up and look it up on your own. But that's what he meant by Butterworth. I mean, those are types of crossovers. Now, you mentioned Laurie, and we mean Laurie Fincham. So we talked about him last week, but that was the first mention of him. So I want to make sure people know who we're talking about. So please go ahead.
Yeah, and in fact, you just mentioned a whole class of different filters. There's all the mathematical functions that we consider for the electroacoustic response to get the right summation. And typically it's Butterworth or Butterworth squared meaning Linkwitz-Riley.
Right.
But we get also fixated on it has to be those, and it doesn't. Basically, there's a whole slew of different kinds of shapes that will add together with the appropriate phase and amplitude relationships to give you what you want. And I actually came up with a methodology that I published in one of the AES preprints that just does away with all of that and makes it very easy, because especially when you're doing three-way systems or four-way systems, and all the filters interact, even the low frequency response of the filter will modify what the high frequency roll-off phase response is and these kind of things. So I came up with improvements to do all of that, which gets away from this limitation that it has to be Linkwitz-Riley.
People normally choose one type over another because of either the slope or the off-axis response or things like that. Now, basically, right? So you're talking about ignoring anything except the resultant sonic results, what you want to have happen with the speakers, right? Or not?
Well, not sonic. It's still a mathematical process. Basically, you want a certain phase overlay between the drivers plus a flat amplitude response. But you get caught up in every time you try and fix one, you make the other worse. And I found a way to separate out the variables, and the answers just fall out really quickly. And you don't even have to go through the calculations of dividing the required result by the driver response. It just gets incorporated in the wash. It's too technical to go into here. Plus, unless you know where my paper is, you don't know how to do it, and I do.
Well, did you publish the paper? Is it still published?
It's published in a preprint somewhere, yes, sir.
Okay, but it's not online anywhere.
I think Laurie discussed it at one point in the chapter in the book he wrote, Loudspeaker and Headphone Handbook, edited by John Borick. This is one of the Bibles that everybody should have on their shelf for speaker
Cool.
design.
Cool.
And it has the most thorough discussion of the design of electrostatic speakers that exists
Wow.
anywhere. Written by Peter Baxendale.
Okay.
And he was a lifelong friend of Peter Walker.
Right.
And when Peter was retiring, everybody was thinking, you should write up about electrostatic design. In fact, Peter offered me a job as he was retiring to understudy and kind of take over, and I was very flattered.
And we're
and
talking about quad in particular.
Quad, yes. And I was very interested in electrostatic speakers, but ultimately I didn't think from a path in the industry, it's maybe too specialized and limited, so I didn't do that. But I'm forever a friend with Peter. But so Peter wasn't going to write all of this work up, but Peter Baxendale did as a commission for the book.
Cool.
And he was doing all sorts of experiments and then talking to Peter and getting every last detail about how it was all done. It's very technical, but a really, really good read. And the whole book is full of stuff like that. And Laurie did a section on crossover design. And in that, he incorporated, I call it the wiggle factor method. And he actually discussed that in there.
That's cool.
Yeah.
That's cool. So when it came to now, you'd had practical experience with the coupled cavity doing that exhaust noise cancellation stuff. So what was the reason? What was KEF trying to solve or resolve by using coupled cavities? What was the whole? What were they trying to defeat or improve on?
So you've got the perennial problem with loudspeakers, passive loudspeakers, that the efficiency, low frequency, bandwidth, and the box size are all kind of interrelated like this. And you can only freely choose two of those parameters, and the third is a given. And typically, for marketing constraints, you've chosen the size of box.
Sure.
And so then you have to make a choice between low frequency extension and efficiency. You can cheat with impedance, which way too many people do, but basically that's the relationship. You've got a little saving grace that the efficiency constant in this equation is higher for a vented box than it is for a closed box. Okay. So you can always get either more efficiency or a smaller box or more base extension from a vented box than you can from a closed box, with the proviso that once you hit that 3 dB point, the cutoff frequency, a vented box rolls off very much faster, twice as fast as a closed box. Yeah. So when you load it in a room and you've got some low frequency help from the room, you'll typically get more help to a closed box than you will a vented box, because the vented box is rolling faster off and the room can help out to a larger degree. So everybody's always trying to think of new ways to improve that efficiency constant.
Right.
And there'll always be a trade-off. Every method that gives you an improvement takes something away. And it's back to, let's decide which is the most important thing we want. And so the thinking behind this idea that had Laurie wanting to look into it is, when you look at the characteristics of a vented box, you have the output of the vent and the output of the driver. If you look at the output of the driver itself, at the tuning frequency, it goes into a notch in its output.
Okay.
That notch is filled in by the vent. The output from the vent is a band pass. Right. So it rolls off second order at low frequencies, rolls off second order at high frequencies. And so it's this kind of mountain peak like that. But it has more low frequency output than the combination itself, because the driver and the vent go out of phase at low frequencies, which is why it rolls off fourth order rather than second. So what if you could just use the vent output and isolate it and not use the driver?
Yeah.
Well,
Cool.
that sounds silly. How do you not use the driver? And so the simple way of thinking about it is, suppose I operate the driver itself into another box. What does that do? It adds a bit of stiffness, because air is stiff.
Sure.
It adds a bit of stiffness to the driver, so we compensate for that. And now we've only got the vent output. So if you think about that, one side of the driver operates into a box, the other side operates into a box which has the vent.
The vent.
That is exactly the configuration of the coupled cavity. And there's subsequent variations of that, of putting a vent on both boxes or a vent in between the boxes, and vents everywhere. But that's the basic premise. And
Cool.
when he researched the idea, we found it had been sort of invented. I don't know if it was patented, but certainly the invention was there around 1954. But no mathematics had ever been done to know how to design. There's a difference between analysis and synthesis. And this is the big thing that Dick Small and Neville Teal did. That you can analyze, you can come up with an equivalent circuit of a loudspeaker in an enclosure and equate it to electrical circuits. And we know a lot about analyzing electrical circuits and calculating what they can do. So if you can do that one-to-one correspondence between the acoustic parts, mass becomes an inductance and a compliance becomes a capacitance and vice versa, come up with that circuit. Now you have a means to analyze and say, well, if these are the masses and compliances and everything, this is what the frequency response will be. And that's very useful because it's particularly, as we know, difficult to measure the low frequency response of a speaker. So to have an alternative method, and with computer optimization these days, which we were doing, we said, at KEF, we could measure the input impedance and optimize an equivalent circuit to that impedance curve. And then we would know precisely what all the responses of that circuit were. And we use that. I mentioned that story about the young engineer that I introduced to Dick. We'd moved away from Teal small parameters because this was more accurate. Teal small parameters were a very useful approximation, but driven by the limits of what we could readily do in the days when all that work started. But what Dick did was find a way with simple mathematics of going from analysis to synthesis, meaning instead of I've got this, what does it do, going to I want this, how do I get it?
Cool.
And
cool.
So that had all been done. Everyone knew how to do it with a closed box and a vented box and whatever, but it had never been done on this concept of a coupled cavity. So the contribution that Laurie did was to get that synthesis process, and that's what was he published in that paper that he gave at the AES that I took away with me and go, aha, this is how I redesign this speaker. And so that became the work. So the idea is that the efficiency constant is a bit higher, and so theoretically you can get a bit more efficiency. The downside is you have a roll-off at high frequencies as well as low frequencies. It is a band pass.
Sure. Yeah.
So it has to be done in the context of a three-way system or just a subwoofer. Yeah. And that high frequency roll-off could be problematical. The impedance curve was particularly problematical because every system at its resonant frequency, the impedance goes very high. So when you take a closed box, it has, at the tuning frequency, the 3 dB down point, it has a big rise in impedance. Now in a two-way system, it's down to back to being normal by the time you cross over at 2 or 3K, so you don't really care about it. In a vented box, there's two peaks. it splits that middle peak into two, one at the low frequency cutoff point and one a bit higher, 100 hertz-ish typically.
Okay.
You don't care about that unless you're doing a three-way system and you're crossing over at 200 or 300 hertz. What you find is designing a passive network to operate into such a complex impedance is very difficult, and you can't get that top end roll off quite right, and so you have to do conjugate load matching. Aha, see, I knew I was going to get there, and I'll get more into it in a minute.
Yeah.
So the idea is you put networks across the driver that compensate for the bump in the impedance to flatten it out. Now you've got back to being close to a resistive load, and
You're talking about a parallel network across the driver itself.
Yeah, a series network in parallel with the driver.
With the driver, okay. Yeah.
And so you can try and flatten out the impedance and make it easier to design the network. And it's particularly important in a coupled cavity because that upper peak is at the upper cutoff point of the system. Okay. So just where you want to cross over is exactly where the peak is.
Where it's going to
be. It was a bugger to do. And so the 1042 was a hugely complex crossover network, partly for that. But so that's called conjugation of the load. Anything that flattens the impedance and the phase curve of the impedance is, designing a conjugate to go across it. So having done that, and when I talk about all this, I was in research peripheral to the product development. I'm talking about a lot of stuff that I didn't do myself,
right?
But I know what was going on, sure, and understood it and whatever. I don't want it to sound as though this was me. It's just my part of this conversation with you about KEF is that I was part of a team that was doing all this stuff, was innovative. And, I contributed more and more as we went through, but, those early days it was, oh yeah, that's cool.
Well, and that speaker was remarkably successful.
Well, it was the biggest selling imported speaker in the US at the time. And there were lots of other features.
And they weren't cheap in those, time. It was a pretty pricey product. Huh?
Yes, I just moved one of them the other day, and you go, oh, this is heavier than I remember. So what I use we often because I'm part of the team, and being a twin, I'm always saying we instead of I. Funny enough, at ELAC, Chris Walker, who's my kind of colleague there, whenever I go out to give talks and technical talks about the ELAC stuff, he would say, don't forget, it's we, not I. It's not all about you, Andrew. So
I've never heard you try and take credit for stuff. You've always been open about the fact that it's anyway.
No, but it was more that when I get talking about technology and design, it's just you naturally fall into I did this because I was doing that. But so we were doing a demo at Crutchfield once, and Chris and I, when we do these trainings together, we're hilarious. We're always ripping on each other, and so he's come up with this spiel that he goes, "Do you know at ELAC on the counter we have a jar? You know what a swear jar is? Where if anyone ever swears, they have to put money in the jar. Well, at ELAC we have an I jar." For Andrew. And whenever he says I, he has to put money in the jar.
Oh.
And then once it fills up, we take that money and we buy him a bar of chocolate. Right? So we've got this thing going on. And then in almost the last presentation we did that week, Chris is saying this again, and as though this was real, I suddenly have this thought, and I stand up and I go, wait a minute, doesn't that really mean I'm just buying my own chocolate?
That's exactly what it means. That's what I thought when you said you took the money and bought him chocolate. I'm like, wait a minute, you're buying your own chocolate. It's crazy.
Okay, yeah. It's funny. Having needed to do quite complex conjugation. I think it was, regardless of what components we needed for that crossover for the bass section on that 1042, we needed an extra 7 or 8 components for the conjugation, and they're big inductors.
I'll
You know,
bet.
like 30 millihenry inductors and crazy things like that.
Okay, well,
So the idea was then, let's take it one step further, because we're always concerned about the impedance of a speaker and how it interacts with the amplifier. Because if the impedance drops too low, you need a lot of current from the amplifier. And in the 70s, going into the 80s, there was a spate of these very expensive speakers that dropped down to stupid low impedances, 2 ohms or 1 ohm. And very often, that
would let the smoke out of the components in a lot of those amplifiers.
Absolutely would. And it was more the fact that since computer-aided network optimization wasn't widespread, you sit there with buckets of components and keep changing them to try and get the response you want. And it's very difficult to both optimize the frequency response you get, the phase response you get, and the impedance. And it's very easy with the wrong ratio of components to get the response you want, but the impedance can just dip low. And ultimately, because if you can't computer optimize, you can't really care about 3 different things all at once. So many speakers just, okay, the impedance is whatever it is. If you need a bigger amplifier, that's not my problem. That's your problem. So ended up having all these big speakers that very low impedance. So then you started to get bigger and bigger amplifiers needing to drive more and more current, which at the same time as driving the voltage or even a bad phase angle in the load means that not only you're driving high peak voltage and high current, in the amplifier, those two, the voltage across the output devices and the current through them are maximized at the same time. So you've had to have output devices that are now dissipating more and more power, which means big heat sinks as well. So these amplifiers just get really, really big. So there'd been a paper produced by Dolby and to study amplifier dissipation with different load characteristics. And basically what they showed is that a resistive load gives the lowest dissipation across the output devices. So since we're already having to conjugate the driver itself before we added a network, we thought, why don't we conjugate the whole speaker after we've finished developing the networks? Instead of putting them across the drivers themselves, although we do a bit of that to help with the crossover design, we'll look at what the final impedance curve is and then put a network ahead of all of that, which gives a flat resistance. And the question is, what resistance? Because you can get a sensitivity advantage by just having a lower and lower resistance, of course, because it's going to draw more current. But what we found is, even making it 4 ohm, if it's resistive, the average power dissipation on music from the amplifier was lower with a flat 4 ohms than a reactive 6 or typical 8 ohm speaker. And so we made it flat 4 ohms. And the other advantage of that was once the resistance is flat, if you drive an amplifier with a high source resistance, particularly a tube amplifier, because it acts as a voltage driver, its source impedance with the load impedance acts as a frequency dependent voltage divider. So you take a tube amplifier and the voltage applied to the speaker is no longer flat. It sort of mirrors the impedance curve. So the frequency response of the speaker can have errors of up to 2 or more dB just because of doing that. So part, I don't want to get into sound of tube versus solid state, but part of most tube amplifiers, they typically have a higher source impedance than a typical solid state. So they interact more with the load. So part of the sound character you hear, if you were to just switch over between one and the other, is that you got a different frequency response from the loudspeaker. So that goes away if you make the speaker a resistive load. So that's what we did. We fully conjugated the speaker. And
that had to be some, I mean, speakers are anything but a purely resistive load. I mean,
yes.
So what you guys did, I mean, I don't want to get off into the weeds here, but I think that's remarkable that you could build what would look to the amplifier as a static 4-ohm load, a resistive 4-ohm load, because I mean, driving a speaker, it's all over the place. I mean, I think I didn't realize that's what that conjugate loading stuff was all about.
Yeah. Now, it's expensive to do, lots of components, and I forget how many components. I know by the time we did the 1053, this was, so at the time, Mike Goff was the chief system engineer, and his last contribution was designing the 1053. Because it was a bit rushed, and we conjugate and then we add a network, then we conjugate and add the next part of the network and keep on going. I think I remember correctly, it was about a 53 element network and enormously complicated. Now, the 1042 was not that complex, but it had to be 20 to 30 components. So
we sold the living crap out of the 104. I mean, I remember playing the 1812, the digital 1812 with the 104s, the Telarc, and so we didn't have a lot of speakers that could do this. Okay, but we put the 104.2s in this room that was right behind. So the store I was in at the time, there was the checkout counter and a glass window behind it looked into one of the main listening rooms, and we had them in there. And when those cans would hit, that glass would, I mean, literally, it would flex probably 3/4 of an inch. I mean, people would sit there and go, is that glass going to break? Those speakers were stupid good in their day. And I don't know how many, I mean, my buddy Steve Rockland built a studio around a pair of them. He loved them so much. He made sure he asked me to tell you that he loved them. So, but that speaker changed, I think, how a lot of people looked at a speaker's size, because it wasn't tiny, but it didn't have a massive footprint for a speaker like it was. Right. Speakers that could play that kind of bass typically in that era were huge, huge footprints.
And the other thing, there were obviously the coupled cavity implemented for that.
Yeah.
It was a double coupled cavity, so two woofers.
Right.
Each had its own back chamber facing into a common
they faced
chamber.
each other, right?
So they did, but one was flipped.
Yeah. Okay.
Right? Okay. Now, that was an interesting exercise because clearly, if you just put magnet to magnet and use the backside of that going to the vent, then you could put a connecting rod between the magnets and do force cancelling.
Okay.
So when we look at, we were talking about needing vibration isolation to minimize cabinet vibration.
Because Lawrence Dickey's kind of doing that now with his Vivids, right?
Yeah, it's a common technique now, but it wasn't common back in 1980s.
No.
And so the idea is, since it's the reaction force due to the cone moving that pushes the magnet back, that's the energy that primarily causes cabinet vibration. So if you can put two drivers back to back, then they're each pushing like that or pulling like that. So putting a connecting rod between them, the net force is zero. So only the cones move. Now you can do that by having one driver on the front of the cabinet, one on the back. But then you've got sound radiating from the back, and it gets awkward. By doing it in the coupled cavity, they both radiate just through the front slot. So that was cool. But the other thing is that if you flip one of the drivers the other way up, then physically, as one cone moves out of the gap. The other one is going into the gap.
Gotcha.
So they're still squeezing air out, double the amount of air of a single driver. But now, distortion,
They're
third order
complementing each
distortion,
other, and yeah.
or second order distortion, gets cancelled. So you get lowered distortion.
Cool.
The problem is, if you want that connecting rod between them, how do you get to the front side of the magnet? You've got to take the dust cap off, connect the rod through, but now you've got a leakage path all through it. So we had that rolling dust cap on the inside of the cone. And so not only that, we then further isolated both chassis. So basically that whole structure, two drivers, the rod, were floating inside the cabinet on vibration mounts.
Oh, I didn't realize that.
Yeah, so it's a very advanced construction. And
I
then
didn't realize
that box on the front, which housed the mid-range drivers,
and tweeter.
because we were into looking at vibration, we knew that chassis vibrate. So those were built with no chassis. We built the box, we captured the magnets for each mid-range onto the back panel of the box, we centered them within the cutout in the front of the box.
Right.
Then we flooded the whole back of that. Well, from the other side, it was a double wall construction, and we flooded it with this rubber compound that acts as a viscoelastic heavy material between the inner and outer walls.
Okay.
And then we built the cones and coils directly onto that cabinet structure. So there were no chassis.
Oh,
So, and then that whole thing floated on anti-vibration mounts from the woofer cabinet.
yeah, I knew that part.
There was a lot of stuff going on in that speaker.
Dude, it was a killer speaker. I mean,
Yeah.
it was one of the first speakers that I actually heard and played with, and it was like, my God. I mean, it was crazy.
Yeah.
I didn't realize there was no chassis behind the mount. I just thought they were mounted in that separate baffle. So the KUBE, what was it? What caused the need for somebody to want to? What was the KUBE created to resolve? What was that about?
So you remember when I talked about measuring, and I said we want to shorten the impulse so that the speaker has finished responding to the impulse before the first reflection comes in, because we want to stop measuring at the point the first reflection arrives.
Yes.
So the first experiments were build a box that can take whatever and this sounds counterintuitive. If we know what the low frequency response is, we can compensate for it and extend it down, we thought, very low in frequency, which will shorten the impulse. And then we can cut the impulse off. Then whatever forcing function, EQ shape we applied before we measured it, we can apply the invoice after we measure it, after we've truncated, and get back to the original response.
Okay.
What we found is that was the wrong thinking. To shorten the impulse, we want to cut it off higher in frequency, not extend it lower. But we'd got this generalized box that we could dial in what we thought was the low frequency response, and then extend it down to wherever we wanted.
Okay.
So once we understood that what we need to do, we just dialed it up to whatever frequency we wanted. So we made everything look like a second order 200 hertz cutoff. And we had techniques for approximating what the low frequency response would be, so it was enough that this technique worked. But we've got this box now that we realize we can turn the low frequency response of the speaker into anything we want it to be, higher or lower than its natural response, matched exactly to that speaker. So that's when the thought, well, we could turn this into a product and either apply it as an aftermarket add-on tuned specifically to that speaker model, i.e. the 1042,
Right.
or we can incorporate it as a necessary part of the speaker system, like the 102 102.3 and 103/2, both
Dude,
of
the
which are
103.2 was a really cool little speaker too. I
yes,
had a pair of those.
yeah, or maybe it was the 103.3 that I became involved with the Cube. The 103.2 was pre-Cube. The
Yeah,
103.3 was
that makes sense. That sounds about right.
yeah, yeah, and so it became one of my jobs was designing these cubes because I'd been working with the basic circuit in research. We're doing measurement, so I got to lay out all the printed circuit boards and come up with the EQ that we needed for specific models. And there's a general form of circuit called a biquadratic that you can use to dial in all the parameters that you need. But it was 4 op amps, and we knew there was this other circuit that was only 1 op amp to do the same job. But the mathematics to synthesize the response were very awkward.
Yeah.
And so one of the engineers, Rick Giccone, he managed to write a program that we could feed in the parameters we wanted, and it would calculate. Because if you got it wrong, the ratio of resistor values were crazy and noise performance was bad. So with that, we were able to then design and build these cubes. And Cube was, Laurie was always good at coming up with acronyms for things. And KUBE was KEF Universal Base Equalizer. And so when we designed the 107.2, that was my first, as I became chief engineer, that was my first reference series product, doing the 107.2. And it used, I think, maybe the first version of the KUBE. And it was integral to the system.
Yeah.
And,
Yeah.
so thereafter we did lots of cubes. Not everybody liked having cubes because it's putting electronics into the circuits or between preamp and power amp or in the tape monitor loop. And the usual story, well, aren't you messing? I've chosen this preamp, degrading the signal path and all this kind of stuff.
Yeah.
So
it damn well worked. I know that.
But it worked, yeah, yeah. And the experiments that led it to being the 107.2 having it first was we left it as a dialable. You can set it to 50, 40, 30, or 20 hertz. Because since it is EQ, you are boosting how much level you're forcing into the drive unit below its natural cutoff frequency. And so you have to be careful about that. So you're able to adjust it back and forth. And that's what led to Laurie producing the paper where we were looking at not only does it extend the low frequency response, but it changes the phase response at low frequencies.
Yeah. Yeah.
So he'd written a paper about the importance of phase response at low frequencies and how, basically the characteristic we heard often, even if there was no obvious deep low bass instruments, you could still hear the effect of changing that low frequency cutoff, even on vocal material.
Sure. Yeah.
An opera singer singing, if it was in a live hall, you heard the sound opened up because the bigger the hall, the more you got a very low frequency noise and sound in there reverberating around, and you got to hear that more clearly. So
I even in the it was the mid 90s that I started this thing, the audio analyst's audio axioms, and one of them was that all you either need a full range speaker or subwoofers that are matched well, because without the information below 30, without say 45 or 40 hertz, the ambience of the hall isn't the same.
right.
And I mean, what you're talking about when you change that EQ setting in that, you're hearing, if it's above 40 hertz, it's not the same. And so, but it changes, it not only affects space, but it does affect tonality of upper mid-range, maybe lower, not so much. I don't know. It does make an effect. I heard it. I had 2 guys that hated the cubes, and I had probably 30 people who loved them. Because they did, if you played with them, you could dial your room in. I mean, it was more
Yeah,
about,
yeah,
in my situation, I believe it was more about matching your room with your speaker
right,
than, playing with an EQ as much as,
yeah.
anything else. So,
Actually, talking about all this, low frequency response and efficiency and box size, it gets into another area of research that I can say I was involved in now because I was finally I get to say
me.
I.
It's all about me.
So, Laurie had become aware of a patent on a technique for faking box size, let's say.
Okay.
So the reason the box affects the low frequency response is that as you compress air, there's a stiffness, it's a
The
spring.
yeah.
And so you're working against that spring. So it raises the resonant frequency and rolls off the response earlier than you would like. So the solution is a bigger box, clearly. But we don't want a bigger box. Can we change the characteristics of air to make the box appear bigger? So,
I've heard about this.
right, so there's something called isobaric versus adiabatic expansion of air.
Okay.
Constant temperature versus constant pressure. And so if you stuff a cabinet with damping material, you can change that characteristic and theoretically get a 40% apparent increase in volume of the air. Now, in practice, you don't get that much, and it's accompanied by much higher losses in the cabinet. So, on balance, especially with a vented box, it's not quite so useful. The advantages a vented box would give you, half of it is at least lost if you overstuff the cabinet.
Sure.
But in principle, you can design the characteristics of a vented box to be perfectly the right cues and response characteristic without any stuffing required in the box, as long as you're not using up to too high a frequency, where you start getting standing waves inside the box. And always the trick is, how do I kill standing waves without overstuffing the enclosure and thus reducing the effectiveness of the vent? That's a whole subject in itself. But anyway, so there's this patent that is using a form of activated charcoal.
That's what it was. Yeah.
And what this does is there's a process called not absorption, but adsorption. And what this does is, as the pressure increases in the air, in the presence of this special form of activated charcoal, the air molecules, actually bond themselves due to the effect of the increased pressure, molecularly bond onto the carbon particles. Wow. So they're essentially lost. They're captured. So with the right kind of activated charcoal, you can theoretically get a 10 times effective increase in the volume of the air.
10 times?
10 times. So
God.
We took a license. The thing about patents is, my first job offer was to be a patent officer in London. I finished my degree, and I can't remember whether it was before I started on that PhD course or when it must have been as soon as I got my degree. I'd seen this advert in the New Scientist magazine, the patent office looking for patent examiners. I thought, that would be cool. Sit in an office, have all these people bring these contraptions for you to look at, and then sort of search through and find out, is this novel and what's different about it. So I actually went down for the interview and found I'd be working in the basement surrounded by filing cabinets, not really meeting any inventor.
Yeah.
You don't have to bring the invention. You just have to have talked
Send a
about
document that explains it. Yeah. Boring.
So they actually offered me the job. So the only job
really?
I've actually ever had to apply for, I actually turned down. But,
well, we're grateful. Thank you.
So this patent was talking about this material. So we
Was it
took out.
expensive to license it? I mean, you had to pay
Oh,
for it, right?
we had to pay. I don't
I
know.
can't imagine.
I wasn't
Yeah,
involved with that
that
part.
was finance. Screw that. Yeah.
Yeah, yeah. Don't
They
worry,
said
Mike.
you can have it. Here you go. You don't care.
Yeah, yeah. So at the time, Dick Small had now started working full time with us.
You
So
say,
the pair of
I'm sorry.
us got assigned to work on this stuff. And there are all sorts of different formulations of this carbon and granule size. And the basic idea is fill the cabinet with carbon powder and remeasure the parameters and see what's happened to the
We
effective.
literally fill it like completely full, or
Sort of.
because it has to, doesn't it have to like be loose enough to move around a
Well,
little bit?
this is the tricky part, and this is the thing about patents. Do they really work? And so we quickly realized that you can't just literally pour it into the
Yeah.
cabinet, because what happens if you move the speaker around? It's going to fall on the cone, it's going to go in the magnet gap, it's going to go everywhere.
In the gaps, in the
Yeah, so we basically made sausages of, some kind of muslin type materials that would essentially trap the carbon, and then we just pack all these sausages inside the speaker cabinet and try and keep them away from the drive units. And we had this special room for this, because this powder gets everywhere. I don't know if you've ever had a wood burning stove.
I have.
So while I was working at KEF, I had this 250-year-old house, and the only form of heating in that whole house was a wood burning stove. And so I used to bring in the logs, stack them around the back of in the ingle nook to dry out, and then you'd load them in the fire. But eventually it gets choked up with all the ash. Yeah. So you need to take the ash out. So what you should do is let the fire completely die down and cool down before you shovel out the ash. But then it's a bugger to get it started again, and it's cold, right? I mean, it's winter time, obviously. So the game used to be, let it die down enough that you can get the shovel in and start shoveling very hot ash and slowly pour it into the bucket, because you had to be slow, otherwise
it was
and the whole house would be coated in dust.
Yep.
So I knew what it was like, and now I'm doing it as my day job. Shoveling carbon and filling sausages, and we used to come out, we had to wear masks, especially for the fire. And we used to, of course, if only we'd had COVID. Now,
this is you and Richard Small, right?
Yeah, if we'd have had COVID then, we'd have felt at home wearing masks all day. Yeah. So we'd come out at the end of the day looking like coal miners, and so we had to be very careful, for health reasons and stuff.
Sure. Now, when was this, Andrew?
Oh, late 80s.
Okay.
Something like that.
Okay.
So maybe straying into the early 90s, because I left in 93. Okay. So it's very late 80s or very early 90s.
Okay.
And we tried forever with this stuff, but we also quickly realized that as good as it is at adsorbing air molecules, it's even better at adsorbing water molecules. And so if you've got any kind of humidity there, that just clogs up all those particles, and you lose effectiveness. So we very quickly realized that without some kind of drying method, it would eventually lose
I hadn't thought of that.
efficiency.
That's interesting.
It also meant we couldn't use it in a vented box.
Because the air,
you let more air in, and also because you filled all the space with these particles that the air's got to get through, it's also very highly damped, so it would also kill the effectiveness of a vent anyway. Yeah. So a lot of what you gain from a vent, you lost by using this material. So you immediately lost half of its advantages. Then you can't get 100% fill, so you've lost another part. And at every turn, the effectiveness of it, even if you use material that itself had a 10-to-1 ratio, you couldn't practically get that out of it. And the 10-to-1 was such a difficult material to use that you couldn't really use that material.
Wow.
So in the end, we kind of gave it up. Now, after I left, so it must
just
have
didn't
been.
seem practical, is what you're saying, right?
It wasn't practical.
Yeah.
Nice idea, and you see DIY people discussing these concepts from time to time, and I just sit back and think, you just don't want to do that.
Yeah,
But
yeah.
KEF did produce one speaker, a very shallow, slim, against the wall type speaker, utilizing this material, but it was only that one model, and that was after I left. And my guess is it was simply to fulfill contractual obligations.
Justify the expense.
Have tried it.
Yeah, justify the expense. Yeah.
Yeah, but it really, in the end, it wasn't. Yeah. It was interesting. Any research is interesting because you learn. My motto has always been, if I knew what I was doing, it wouldn't be research.
Yeah,
so
that's true. Yeah.
It was interesting, but ultimately fruitless.
Yeah. Now, I guess let's try and get into the Uni-Q story a little bit. As I mentioned in the intro here, when you look at it, I mean, when you step back and go, oh, the launch, what a great idea. Mm-hmm. Now, but nobody had really done it before that, had they? Or had anybody because the issue is getting that driver motor to work inside the other motor, and to get it all aligned. It had to do with the what's the word for magnetivity? The ability to get a magnet that was strong enough to do it, right?
The concept. First of all, why would you want to do it in the first place? Why would you want a concentric driver?
I think that makes perfect sense.
And so we go from what is the theoretical ideal loudspeaker, and we could say a single piston that covers the whole frequency range, goes low enough, goes high enough, can play loud enough. Yeah. So the perfect piston or the expanding sphere. There's in theoretical acoustics, let's say three fundamental radiators: expanding sphere, oscillating sphere, or piston, moving piston. And mathematical solutions exist for all of those. When you get more complicated, the mathematical solutions aren't always readily available.
Well, and Nelson Pass will tell you that the ion cloud just about killed him because of all the ozone.
Oh, I mean, I've spoken about this in other interviews, in fact. So when I was reading, I'm definitely still at school at this point, I think. I'd read about him experimenting with that ion cloud thing.
It was the early 80s, right? That was like 81, 82, something like that?
No, I think it has to be earlier than that.
Oh, really? Okay. Yeah, I was thinking it was like 82-ish for some reason. Because I think he showed it at CES in 82.
Oh, maybe he showed it, but
he was working on it earlier than that, yeah.
Yeah, maybe it wasn't him. I'd read the original paper by Towns on doing this.
Oh, okay.
And so I thought, this would be cool to play with. So I was home from school or university one time, and I thought, how do I see whether it works? Well, I've got that zero-stat pistol, and the zero-stat squirts ions out, right?
Yes, it does.
So I now have my ion source. Now I need a high voltage supply. Well, while we were at school, we used to go around electrocuting people all the time. We got transformers, ran them backwards, got a battery, and we'd keep tap, 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 tap. And we'd wire door handles and things and give people electric shock. Even to the sixth form.
Glad I didn't live in your dorm when I was in school.
Even in the sixth form common room, we wired the door handle. And one of the teachers got caught by it. And the general answer is, now boys, don't you think you've had enough fun? I mean, these days you'd be immediately expelled for this. But
that's funny.
So we knew how to create high voltage, but England versus the US, our line voltage is 240 volts, not your wimpy 120.
Yeah.
So I got some grills off a transistor radio. So squares about that big. So I've placed them, quarter of an inch apart, trying to be careful not to let them short together, because one I plugged into live, the other into neutral, straight into the socket. And then I got my zero stat pistol and I'm squirting it in the ground. I'm trying to listen. Now this is going to be a very distorted signal, but nonetheless, I'm squeezing the zero stat in, and I think I can hear this 50 or ish hertz buzz, but it's very quiet. So I'm getting closer and closer and closer, and I got my ear about that far away from 240 volt plugged straight into the wall. So fortunately I survived that one as well. Anyway, so yes, that's the other theoretical radiator. We just digressed.
Sorry, that's funny as hell.
So we go to that theoretical radiator. Now we say, well, we can't practically meet those requirements because we have to move a large physical volume of air at low frequencies, but slowly. High frequencies, we need to move only a small amount of air, but very fast.
Yeah.
Those two requirements, to move that much air, the piston has to be quite big, which means it's heavy, means it can't respond fast. So there is no practical full range speaker, single drive unit. You got.
Amar Bose thinks there is. Oh, sorry.
No,
and another way. I'm sorry.
So we do a minimum split it into two, so the typical two-way system. I've forgotten where we were going with this. Why we were talking about Uni-Q. So we've now got a two-way system. We've optimized the drivers to cover the high frequencies and low frequencies. So we've got full range, relatively full range operation.
Relatively full range, yeah.
But we've lost something. We've lost the fact that it's a single radiator. And what has that done? Well, the spacing causes three problems. The first is we are sensitive to sound elevation. We know the birds are singing up there, and we know something is going down on our feet.
That air brain mechanism is pretty well developed to determine directionality pretty easily.
Yeah. Now, we're not as clear on vertical direction as we are horizontal, because we've only got, the ears work to get the same way for vertical, whereas they work sort of differentially for horizontal. But nonetheless, we have elevation sensitivity. So we've now split the sound into two parts at different heights. And so sort of fundamentals are coming from one driver and harmonics from the other, and we're somewhat sensitive.
Yeah, we're aware.
We're aware. Then we've got the fact that as we stand up or sit down, our effective distance from each driver changes. So since through the crossover region, the phase relationships between the two drivers is critical, that phase relationship has now changed because of the different distance, and so the response changes. And then the third thing is speakers or any sound source is directional once it becomes comparable to the wavelength of the sound. So at low frequencies, all sound sources are omnidirectional. At high frequencies, they're all beam. Just like taking a flashlight, focusing flashlight, wide beam, narrow beam. Since the two drivers are different sizes, as we already said, the requirements need them to be, their directional characteristics are different in the frequency range where we cross from one to another. So even if we match the sound in the forward direction, it won't match fully off axis through the crossover point. So we've now imposed these limitations by splitting into two drivers. We've gained on one hand and lost on the other. The concentric driver recognizes this and says, well, let's put them on the same axis. But not just on the same axis, but we move that tweeter in until it's at the acoustic center, essentially, of the bass driver. So now they're aligned.
Centers of both drivers are the same. So you've got almost a single point. You've duplicated that option for a single point source.
So now it can't change. The phase relationships between the two can't change when we move around the speaker either vertically or horizontally. And the third part is that since the cone acts as a waveguide for the tweeter, we can match the directivities through crossover between the two drivers. So now off axis we'll just get a smooth falling off
Okay.
in power response and off-axis response compared to having the separated drivers.
Okay. Yeah.
So we fixed all that. We've lost something. This concept of, well, this waveguide is kind of moving back and forth around the tweeter. Won't that cause issues? Yes, it can. In the limit, it can, if you do it enough, can cause a bit of Doppler distortion. We apparently
But
are.
I mean, yeah, how much are we talking? Like, you know, an eighth
Well,
of an inch, a quarter of an
well,
inch?
if you're going
Yeah.
to do it with a, try and make this bass driver go down low enough, it can be moving easily a centimeter
Really? Yeah.
peak to peak,
Okay.
maybe a bit more.
All
So that can conceivably cause, well, will cause Doppler distortion. The question is, how sensitive are we for Doppler distortion? And there's, different people have different opinion on this. And when we were investigating this, because, this is something we recognized if we're going to do this, of course, it solves, so let's just go back a minute. It solves all these three problems, right?
Yes.
Now, it's not the first time a concentric or coaxial driver had ever been done. They've been around since the 40s and 50s. And think of tannoy.
Yep.
They've always had their dual, they call it dual concentric.
Right.
The only difference is the way they constructed it, because of the availability of magnets, it required them to use a compression driver at the back of the bass driver and fire all the way through the pole piece as part of the waveguide and out through the cone and out. What prompted?
That would have messed with the acoustic centers of both drivers, right? I mean,
well, now they're still not aligned that way. In fact, the tweeter is behind the woofer.
Way behind. Yeah.
Whereas in most conventional speakers, it's in front, right?
Right.
So, in looking at that, Laurie had been inspired because of reading about neodymium magnets. So when we look at energy density of magnets, we find that ceramic, if you made it small enough, step back a bit, what we want to try and do is align those two drivers.
Correct.
That means since the woofer voice coil drives through the voice coil former, connects to the cone, and then starts radiating. The speed of sound through that is very fast. It's faster than air. So the voice coil is not actually the acoustic center of the driver. It's more the apex of the cone and the dust cap.
Sure.
Disregarding bandwidth limitations of the driver. So if we could mount the tweeter dome right at the apex of the cone, everything's time aligned and we're good to go. But the magnets weren't appropriate at that time for doing that. But reading about neodymium gave Laurie the idea that maybe we can shrink it enough to sit it on the top of the pole piece of the woofer, so the dome of the tweeter is aligned with the apex of the cone. And so the early experiments were done with, what's the magnetic material? Alnico. Because when you design a magnet circuit, ferrite needs to be large area and not very deep. Alnico needs to be small area but very deep. So that aligned perfectly with fitting it in the voice coil. If we reconstruct the drive unit to have a very long voice coil former initially to try this idea out. So it was tried with Alnico, and the efficiency was not that great, but it was to test the concept. And then the idea was, as the neodymium becomes available to us, which required having it specially tooled to make a magnet of the exact size and shape that we needed, then we can shrink everything down, get good efficiency, put it on top of the pole piece, come up with a way to get it properly centered in the gap so you don't get it rubbing against the voice coil. Now we have a concentric driver that has the acoustic centers aligned. And so that became Uni-Q. And again, I was not involved in that initial work or the design of the speaker systems, but I was peripherally involved, like I discussed last time, with the research project of looking at room acoustics. So I was building concentric driver speaker systems for research purposes.
Okay.
And Uni-Q, again, one of Laurie's acronyms, which was
What did it stand for? I never knew.
So
I
Uni.
assume the Q had to do with the electrical capabilities from Q, like a speaker Q.
No,
No?
in fact, no. Uni means one.
Okay.
Q is the symbol for directivity constant when you
Oh.
look at the ratio between on-axis and power response of a
Oh.
driver. So Q is
Okay.
directivity. So it's one directivity.
Cool. All right.
Yeah, really cool.
Yeah.
So that's what became incorporated into the Uni-Q line of speakers.
So I think it should be clear to anybody that's been watching this, because I've had the good fortune of talking to Laurie a couple of times on different projects. The guy's a monster. I mean, he's had so many of his ideas or his design, his initial impressions become real products. Did Raymond Cook hire him?
Yes.
I mean, how did Laurie come to KEF? Do you know that story? I mean, he's been around for a long time, but when did Laurie come?
I believe he came from Goodman's. I know he worked at Goodman's and did work there, so I think he was hired from Goodman's to come to KEF. We should get him on. I should try and get you an interview with him.
I'd love to. You know, the last time I spoke with him, or I didn't speak with him, I exchanged emails, was when I can't remember exactly what his role was with the benchmark AHB2 amplifier.
Yeah, that was, so when he went to THX, you know, this is for later in the series.
That's how it came.
So he became head of research at THX.
Yeah.
He hired my twin brother to do all the electronic design for him. So my brother came up with the topology for that AAA amplifier.
Okay.
Developed it to be licensed by THX, and then Benchmark took that license.
Yes.
And my brother basically worked with them to design that amplifier. So all of that power amp circuit is my brother's implementation. He actually did, but not just license the technique and advise, but he actually designed that circuitry for that amplifier.
That's very cool. That's amazing.
So, yeah, Laurie was brilliant. He was a polymath, as a lot of people, you know, are. Yeah, I only know speakers. I did it all my life.
And you know them pretty damn well, sir. I'm telling you. We've been running on for quite a while. I'm sure people are everybody loves hearing you. I mean, it's a blast to listen to you, man. I love these stories. But I think we should try and wind this down for this particular episode. And I'm curious. So 80, you came in around 83 and you left around 93? Something like 93, 94? 94. So what, without getting into too much of the next topic, what pulled you away from KEF in 94?
So KEF were not doing so well, and they'd actually sold.
This was Gold Peak Holding?
Yeah. Gold Peak, Kinergetics, there's all these different holding companies that were involved. And they had already, although I didn't know it at the time, they'd already purchased Celestion.
Right.
And, you know, I knew of Celestion. Obviously, we used to meet at all the lectures, and I knew Graham Bank quite well. And we'd said earlier about my postgraduate research. So Celestion were a partner for that research in providing facilities. I don't know if they provided money, but they provided facilities and drivers. So I knew Graham Bank back from those days. So they had already purchased Celestion. They purchased KEF. And so they installed new management. And yeah, I got to know a couple of the owners, the new owners, pretty well. Nice guys. But because all this was new, the idea was to try and do as much squishing the two companies together as possible to save money. Why do you need, for example, two purchasing departments?
Let's overlap.
So, and they brought in as the new managing director, the existing managing director of Celestion. And we thought that was, oh, why would he come in?
For God's sake, why would
They
we
were
want
our rivals, and then, so I think, to be honest, we weren't happy. Whenever companies
Sure.
change,
Yeah.
it's unsettling.
Well,
And,
nobody likes change, but
and sometimes change, even forced change, turns out to be good. You just don't know it at the time.
never know.
And so we weren't happy. And I know Laurie Fincham was approached to move to the States. And then Dick Small, he decided to leave. And gradually people were leaving. And then someone new came in to run
Yeah.
the department, in the absence of Laurie, who's going to be in charge of the department. And they brought in another guy to do that. And it was, I know I had a year where in this transition, there was no product being designed.
Wow.
So I was happy because, in one respect, because I'll just do some research.
More research. Yeah.
And there's various aspects of the Uni-Q that have been bugging me in performance. So I spent a whole year just working on new concepts for how to do a better concentric driver. So it was a productive time for me, but it was still an atmosphere that wasn't so enjoyable. And so I was approached to move to the States as well. And
that
so,
was initially, you went to Infinity first?
yes,
Okay.
yes.
Okay.
In
You weren't
fact,
there very long, just a couple of years, right?
I think about 3 years, just under 3 years, but working with Laurie again, because that's where he'd gone. And I was happy for him to see
I'm sure.
what the States was going to be like before I committed myself to it.
Well, that's where we will pick up again.
Okay.
Andrew, I can't thank you enough. It's always a blast, man. Love hearing you tell these stories. We'll pick up again with the Infinity story, which hopefully will take us through Infinity, Pioneer, and the TAD years.
Right. That's a lot to get in as well.
Buddy, you're really wonderful to help me try to do this. So I'm grateful for doing it because I think people really want to know this stuff. So
yeah. Okay.
But for now, thank you again for joining us, and we'll talk again very soon.
All right. Thanks for having me. Cheers.
What a great conversation. I can't thank Andrew enough for sharing all his history with us today. I not only sold, but owned and used many of the products we spoke about in today's episode. So it really makes this a special episode and makes it especially interesting. Next week, he will discuss his time with Infinity, Pioneer, and TAD from the 2 decades between 1994 to 2014. With that, I'll remind you that if you find any merit or value in the information I'm sharing here, please subscribe, like, and share links to your episodes with your friends. And I love hearing from you, so be sure to leave your comments and questions in the comments section below. And you may support the channel using Patreon, Venmo, or PayPal, or even by securing display advertising at the Audio Analyst website. And links for all options are provided in today's description. As always, thank you so much for taking the time to drop by and visit today. Please be sure to stay safe and keep the music playing. Till next week, cheers.